Right now, city planners down in Miami are, well, they're trying to figure out how many billions of dollars to spend on future seawalls.
Right.
And over in California, you've got water managers who are calculating exactly how much they can safely draw from these shrinking reservoirs over the next, like, 2 decades.
Yeah, massive decisions.
Exactly. These are civilization-defining choices, really. And to make them, they are relying on a computer program. But, and this is the crazy part, unlike those, fiercely guarded trillion-dollar algorithms out of Silicon Valley or some classified software inside a stealth bomber, this program wasn't built by a corporation.
No, it wasn't.
It wasn't been built by a spy agency either. It was built by a public lab.
Yeah.
And they gave it away completely for free.
Yeah, it really flips our whole modern expectation of, technological advancement totally upside down.
It really does.
Because we are so conditioned, societally, to believe that the most valuable intellectual property has to be locked behind these heavy corporate doors.
With a massive price tag attached, right?
Exactly, a huge price tag. But what we're looking at today proves that the complete opposite can be true.
So we're talking about the most sophisticated, complex computer simulation of our entire planet that exists anywhere, basically a virtual Earth. And today, our mission for this deep dive is to explore just this astonishing stack of source materials detailing how this even happens.
It's quite a stack.
It is. We've got historical archives from the National Center for Atmospheric Research, that's NCAR, out in Boulder, Colorado. We've got scientific papers dating all the way back to 1967.
Some really foundational stuff.
Yeah, and then we're looking at supercomputing hardware specs that honestly just melt your brain. And crucially, we have these recent news reports from late 2025 and early 2026 detailing this massive, looming political battle over the future of this very model.
Right, and just to set the framework here before we really dive in, looking at those recent news reports from 2025 and 2026, we see a very significant political fight brewing over the funding and really the management of this model.
Yes, very heated.
But to be totally clear to you listening, we are just looking at the structural facts here. The historical timelines laid out in these documents. Regardless of the politics behind the debate, left or right, our goal today is simply to understand the structural role this model plays in global science.
Right, impartially reporting on what the sources say.
Exactly. We just want to explore what it actually means to manage a scientific tool of this scale as a shared resource.
Right, we aren't taking sides on the policy fight at all. We just want to explore the architecture of the tool itself as described in these documents. So, okay, let's unpack this. How do we go from, a couple of guys in a basement to literally thousands of scientists sharing a virtual Earth?
It's a huge leap.
It is. And to understand the sheer scale of the community model today, I realized looking at these sources, we really had to go all the way back to 1963 because, well, before you can model ocean currents or space weather, you have to figure out how to put the sky into a machine.
Yeah, and in 1963, doing that required a level of audacity that is just, well, it's hard to overstate.
I can imagine.
Which brings us to Warren Washington. He had just arrived at the NCRR Mesa Lab in Boulder, and he was hired fresh out of Penn State, where he was actually the second African-American to ever earn a doctorate in atmospheric science.
Wow, so a brilliant mind walking into an almost impossible problem.
Exactly. And he teams up with Akira Kasahara, who was this highly respected Japanese-American meteorologist from the University of Tokyo's theoretical program.
Okay.
So they find themselves in this basement room at the Mesa Lab in the early 60s, and they just decide they're going to build a general circulation model of the entire global atmosphere.
Which is wild because I was reading the hardware specs for what they were working with, and my brain kind of short-circuited a little bit.
Oh, the old computers.
Yes, they used a CDC 6600, which was delivered by Seymour Cray in 1964. The sources say this machine was literally the size of a garage.
Yeah, it took up a whole room.
And it required these massive, complex cooling systems. Yet, my smartphone, the one sitting on my desk right now, has exponentially more processing power than that. I mean, I can't even get my phone's weather app to load quickly half the time.
Right.
So how do you model the entire global atmosphere with a machine that has relatively speaking, less computational muscle than a modern digital watch.
Well, you do it through just radical simplification and really brilliant mathematics.
Okay, how so?
They knew they couldn't simulate every single cloud or, every individual gust of wind. That's impossible. Instead, they had to translate the sky into geometry.
Geometry.
Yeah. Imagine taking the Earth and wrapping it in a wire mesh, and then you stack several layers of that wire mesh miles up into the sky.
Oh, I see. So you're basically chopping the entire atmosphere into millions of three-dimensional boxes.
Exactly. A massive 3D grid. And for each one of those individual boxes, you assign a set of fundamental physics equations.
Like what kind of equations?
Mostly fluid dynamics and thermodynamics. You basically ask the computer to calculate, okay, how much heat is in this specific box right now? What's the pressure? What is the moisture level?
Right.
And then, based on the laws of physics, how will that heat and momentum transfer to the box immediately next to it in, say, the next 10 minutes?
Wow. So it's essentially this giant planetary mathematical ledger.
That's a great way to put it, yeah.
But even if you simplify it to these grid boxes, calculating the physics for the whole planet minute by minute on a 1960s computer, I mean, that must have taken an agonizingly long time.
Oh, it was incredibly slow. I mean, they were wrestling with physical punch cards, and the programs were just constantly crashing.
Gift cards, just to simulate the wind.
Yeah. But the real breakthrough finally came in 1967. Washington and Kasahara published this landmark paper in the Monthly Weather Review, and it was titled NCAR Global General Circulation Model of the Atmosphere.
Now, I notice the sources make a massive distinction here, which I think is super important. This paper was not a weather forecast, right?
No, not at all.
Like, they weren't trying to tell someone in Chicago to bring an umbrella on a Tuesday.
That is a very vital distinction to make. What it was really was a demonstration of principle.
Okay.
What their 1967 paper proved was that a computer could successfully reproduce the macro-level features of our planetary system spontaneously.
Spontaneously? What do you mean by that?
Well, they didn't write code that explicitly said, put a jet stream over North America right here.
Oh, I assume they did.
No, they just gave the computer the basic underlying laws of fluid dynamics, started the simulation, and the jet streams naturally formed in the virtual sky all on their own.
Wait, really?
Yeah. The trade winds emerged. Those massive Hadley cells that transport heat from the equator toward the poles, they all just generated themselves because the underlying math demanded it.
Okay, that is the part that honestly gave me goosebumps reading this. The physics were so sound that a virtual Earth essentially just woke up and started behaving like the real one.
Exactly. It mirrored reality.
But what stopped them from just, keeping this incredible tool to themselves?
Well, what's really fascinating here is that NCR's entire institutional DMA was just fundamentally different from other labs at the time.
How so?
They were funded by the National Science Foundation, the NSF, and they were managed by a consortium of universities called UKR. So they weren't a government operational agency like, say, the National Weather Service.
Right, whose job is to issue daily public alerts and warnings.
Exactly. NCR's specific mandates, the reason they existed, was to serve university researchers.
So their mandate was literally to build tools for other people to use.
Precisely. And that unique mandate is really what set the stage for the great philosophical leap of the 1980s.
Which the sources highlight as a huge turning point.
Right. So throughout the 70s, computers are getting faster, the grid boxes they use are getting smaller, and scientists start adding these things called parameterizations.
Okay, yes, I hit this word a lot in the source documents. Parameterizations. So my understanding is if a grid box is, say, 100 miles wide, but a cloud is only a mile wide, the computer can't actually see the cloud, right?
Correct. It's too small for the resolution of the grid.
So a parameterization is basically a cheat sheet, like a mathematical summary you give the computer so it knows how clouds should behave inside that giant box, even without simulating every single drop of water.
A cheat sheet is a really good way to think of it, actually. It's an approximation of small-scale physics.
Got it.
But writing those cheat sheets requires an immense amount of localized expertise. And that leads us to 1983. NCOAR releases the Community Climate Model, the CCM. And they make this decision that honestly altered the course of scientific history.
They gave the code away.
They gave it away for free to the entire university research community.
I was really trying to contextualize this because, today we have things like Linux and open source software. So giving code away sounds pretty normal to us now.
Right, it's very common now.
But in 1983, the sources note that other major groups like the Geophysical Fluid Dynamics Laboratory at Princeton or the UK Met Office, they treated their models like locked vaults.
Very heavily guarded.
Their code was their proprietary institutional property.
Mhm.
So why did NCRR just suddenly open the doors?
Because they had this realization that the Earth is just too complex for one building full of scientists to figure out.
Makes sense.
By giving the model away, they effectively created an intellectual commons. Now, it was sort of an informal expectation at first, but it quickly became a structured reality. The deal was, if you take our code, run it at your university, and your brilliant graduate students figure out a better parameterization for, say, how sunlight bounces off sea ice.
Then you give that improved code back to them.
Exactly. You share it back with the central hub.
So it's less like an institutional product and more like almost like a massive Wikipedia page for the laws of physics.
That's a fantastic analogy.
Because thousands of scientists all over the world are just constantly editing it, refining it, and adding new chapters. So a university professor down in Texas might spend 4 years perfecting exactly how soil absorbs water, and maybe a team in Germany spends 3 years perfecting how radiation moves through the stratosphere, and it all just gets merged into the same master code.
That wiki analogy captures the compounding returns of this approach perfectly. The code base literally became this living repository of human understanding.
Wow.
But as revolutionary as the community climate model was in the 80s, it had a fairly fatal flaw if you wanted to accurately look into the modern future.
Which was?
It only looked at the sky.
Right. And I was kind of stuck on this while reading through the 1990s archives. Because modeling climate change without the ocean seems, well, pointless.
It does seem that way now, yeah.
I mean, I understand they had computing limits back then, but the atmosphere is just this thin layer of gas. The ocean holds all the real heat.
The ocean is the massive flywheel of the entire planetary system. It entirely dictates the long-term memory of the climate. Right.
You simply cannot understand what the atmosphere is going to do over a 50-year period without knowing what the ocean is doing underneath it.
So skipping ahead to 1994, the NCR scientists put forward this proposal to the NSF to build a fully coupled climate system model.
The CSM, yes.
They want to take this world-class atmospheric model and stitch it to an ocean model, a land surface model, and a sea ice model, all running at the exact same time, constantly talking to each other.
And that talking part, the communication between the models, is the hardest part by far.
Because of all the data.
Exactly. You are passing massive amounts of data back and forth between different physics engines at every tiny time step of the simulation. When they first tried this in the early days, it was a complete disaster.
Really?
Oh yeah, the simulated climates would just drift completely into chaos.
Right. The sources talk about the models just crashing. The oceans would slowly freeze totally solid, or the tropics would completely boil over. And the reason wasn't global warming, it was just the math, right?
It was entirely the math. Because these tiny, tiny errors between the ocean code and the sky code would just compound. It reminded me of like a tiny rounding error on a mortgage that balloons into millions of dollars over a 30-year loan.
That is a great way to visualize what they call model drift. So to stop the models from spiraling into a frozen or boiling mess, scientists in the early 90s relied on something called flux adjustments.
Okay, I really want to dig into flux adjustments here because the sources frame the elimination of them as one of the greatest scientific triumphs of the decade. So what actually is a flux adjustment?
It is essentially an artificial fudge factor.
A fudge factor.
Yeah. So if your model's ocean is bleeding heat into the atmosphere too quickly because your equations aren't perfectly balanced, the virtual ocean gets colder and colder over time.
Right, and eventually freezes.
Exactly. So to keep the simulation stable enough to actually study, the programmer manually injects an artificial pulse of heat into the ocean surface.
Wait, really?
Yes. You are literally patching the math with fake energy just to keep the virtual Earth alive.
But, I mean, if I'm a skeptic looking at that model, my immediate question is, if you have to pump literal fake heat into your virtual Earth just to keep it from breaking, why should I trust what it tells me about real-world global warming?
And you would be entirely justified in asking that. In fact, that was the central critique of early climate modeling.
I can see why.
So that 1994 proposal was just incredibly ambitious. They declared they were going to build a coupled model so physically accurate and so perfectly balanced across all four components that it would not require a single flux adjustment.
No fudge factors at all.
None. They were going to force the physics to be right.
And when they finally released the model in 1996, they actually did it. The simulation balanced its own energy budget naturally. The virtual Earth could sustain itself,
It was a massive achievement.
which paved the way for the next massive upgrade. By 2010, the model evolves again into CESM 1.2, the Community Earth System model. So
Yeah.
we go from a climate system to an Earth system. And the key addition the sources talk about here is interactive biogeochemistry. What does that actually mean for the code?
It means the model transitioned from just calculating physics, wind, heat, water, to actually calculating life.
Life.
Well, at least the chemical impacts of life. They integrated the carbon cycle.
Okay, but how do you code a tree into a fluid dynamics model?
You build a complex parameterization for vegetation. So the model looks at a grid box over, say, the Amazon rainforest.
Right.
It calculates the sunlight hitting that box, the soil moisture, and the temperature. And then, based on those inputs, the code calculates how much CO2 the virtual canopy breathes in through photosynthesis and how much water it sweats out through transpiration.
That's incredible. And it does the same for the ocean, right? The sources mentioned the biological pump.
Yes, the microscopic plankton. The model calculates plankton blooms based on ocean temperature and nutrient upwelling.
Okay.
And when those virtual planktons die, the math actually simulates them sinking into the deep ocean, dragging the carbon they absorb down with them, sequestering it away from the atmosphere.
This is where my mind truly gets blown. Because by adding this biogeochemistry, the model creates a totally closed feedback loop.
Exactly.
You aren't just telling the computer, hey, CO2 is rising, make it hotter. The computer makes it hotter naturally, and then that heat dries out the virtual Amazon rainforest.
Right.
And then the dry virtual trees absorb less carbon. That leaves more CO2 in the virtual sky, which makes it even hotter, which changes the ocean current, which kills the plankton, which stops the ocean from absorbing carbon.
It's the chain reactions. The model is simulating the exact holistic cascading chaos of the real world.
Which brings us to the most practical question for you listening. We have this staggering piece of shared infrastructure.
Yeah.
Thousands of scientists editing the physics of a virtual Earth. But what do we actually do with it? Like, how does this impact someone listening to this deep dive right now?
Well, we use it to peer into the chaos that threatens our lives, really. We use it to map the boundaries of extreme weather.
Let's start with hurricanes then, because the dossier has some fascinating data on this. Researchers use a high-resolution version of the model called CESM-HR, where they shrink the grid boxes way down. The atmosphere boxes drop to 25 kilometers, and the ocean boxes down to like 3 to 10 kilometers.
Right, and by shrinking the mesh that much, you can actually resolve the distinct eye of a hurricane and the intense thunderstorms of the eye wall right inside the simulation.
And the findings are absolutely crucial for anyone living on a coast. The model shows that in a warming world, the intensity of hurricanes, meaning the sheer wind speed and the sheer volume of water they dump, that goes up.
Yes, significantly.
But here's the paradox I really need you to explain. While the intensity goes up, the model suggests the total number of hurricanes globally might actually drop, or at least just stay the same. Why does the model predict fewer storms, but worse storms?
It's a beautiful example of competing physical forces, and it's exactly why we need models that calculate everything at once.
Okay, unpack that.
The intensity increase is just pure thermodynamics. Hurricanes are massive heat engines. They feed on warm ocean water.
Right, that makes sense.
So as global sea surface temperatures rise, the fuel for that engine becomes much, much richer. The thermodynamic ceiling is lifted. So if a storm does form, it has the energy to pull in vastly more moisture and spin at devastating speeds.
Okay, so the fuel tank is bigger. That makes perfect sense for the intensity part. But why fewer storms forming in the first place?
Because the fuel is only half the equation. You also need the spark, right? The ignition.
Okay.
For a tropical wave to actually organize into a spinning cyclone, the atmosphere has to be unstable, and crucially, you need very low wind shear.
Wind shear.
Yeah, wind shear is when the wind at the surface of the ocean is blowing in a different direction or at a different speed than the wind high up in the atmosphere.
Oh, I see.
If wind shear is high, it literally rips a developing storm apart before it can even get organized.
So what does the model show happening to the shear in the future?
The model calculates that as the broader climate warms, the tropical atmosphere might actually become slightly more stable, and wind shear in key development zones, like the main region of the Atlantic, might actually increase.
Really?
Yeah, the environment becomes fundamentally more hostile to a storm getting organized. The ignition gets harder to spark.
So basically, 100 tropical waves might roll off the coast of Africa, and 99 of them just get completely ripped apart by this new hostile wind shear.
Exactly. But that one storm that manages to fight through the shear and get organized,
Yeah.
it suddenly taps into an ocean that is supercharged with heat, and it explodes into a total monster.
Wow, that distinction. Fewer storms, but the ones that survive are catastrophic. I mean, that completely changes how emergency managers have to plan for evacuations.
It really does.
Let's pivot to the American West and Southern Europe for a second. Wildfires and drought. The model projects enhanced aridity in these regions. But reading the sources, it's not just a lack of rain causing it, is it?
No, it's mostly driven by something called evapotranspiration.
Evapotranspiration.
Yes. And this is where the coupled land-atmosphere system is vital. As the baseline temperature goes up, the atmosphere itself physically changes. It becomes a thirstier sponge.
A thirstier sponge.
Yeah, exactly. Even if the amount of rain falling on California or Spain remains exactly the same, the hotter air literally pulls moisture out of the soil and out of vegetation at a much faster rate.
And that dry vegetation is exactly the fuel for the mega fires we see dominating the news every summer.
Precisely.
The sources note that water resource planners use this specific model data to predict the future flow of the Colorado River.
Yep.
It's not academic at all. It's literally the survival math for the Southwest.
It absolutely is. And the beauty of the model is its ability to find these complex connections we wouldn't see otherwise.
Which perfectly tees up what I think is honestly the most mind-bending discovery in the entire dossier.
Oh, the ozone hole.
Yes. It involves the ozone hole over Antarctica.
Okay.
So they used a high-top extension of the model called WACCM, the Whole Atmosphere Community Climate Model.
Right.
Now, I understand that human chemicals, like CFCs, punched a hole in the ozone layer. We all learned that. But the model showed this hole actually changed ocean currents near the equator. I stared at this part of the source material for like 20 minutes.
It's unintuitive, I know.
It is. How does a chemical hole in the sky over the South Pole change the temperature of the water in the tropical Pacific?
It is a stunning Rube Goldberg machine of planetary physics.
Okay, walk me through it.
Let's trace the cascade, step by step, exactly as the model computed it. Step 1. The ozone layer's job is to absorb ultraviolet radiation, which naturally creates heat.
Okay.
When you destroy the ozone with CFCs, the lower stratosphere over Antarctica loses its heater. It cools down significantly.
Okay, so colder air high above the South Pole. Got it.
Step 2. Because that air is now abnormally cold compared to the air further north, the temperature gradient steepens. And this physically strengthens and tightens the polar vortex, which is the massive belt of wind that constantly circles Antarctica.
So the wind belt pulls tighter like a drawstring.
Exactly, like a drawstring. Now, step 3. That tightening physically pulls the southern hemisphere's mid-latitude winds further south.
Okay.
Step 4. Those winds are now blowing over a completely different patch of the Southern Ocean. They drag on the surface of the water, and that alters the massive ocean circulation currents.
So the wind is literally pushing the ocean differently just because the sky got colder.
Yes, exactly. And step 5, that altered ocean circulation changes how deep cold water upwells to the surface along the coastlines. And that upwelling of cold water eventually propagates all the way up into the tropical Pacific Ocean.
And changes in tropical Pacific water temperatures are exactly what cause El Niño and La Niña.
You've got it. The model proved that the ozone hole promoted a cooling pattern in the Pacific that strongly resembled a La Niña event.
It is wild.
Which, in turn, altered rainfall patterns all the way from Australia to South America.
I just have to pause and marvel at this for a second. A human scientist didn't sit at a desk and guess that 1980s hairspray was causing droughts in South America by shifting wind belts over Antarctica.
No, they couldn't have guessed that.
The model discovered it. They plugged the chemistry into the skybox, the wind into the middle boxes, the water into the ocean box, hit run, and the virtual Earth just revealed this hidden gear in the planetary machine.
That is the ultimate validation of the open commons we talked about.
Right.
You have a chemist from MIT writing the ozone equations, an oceanographer from Scripps writing the water current equations, and a dynamicist from Oxford writing the wind equations. They all contribute to the shared code base. So the discovery belongs to the collective intelligence of the community.
And the sources show they're pushing this even further now, right? They are modeling near-Earth space weather, coupling the upper atmosphere to the lower atmosphere to actually predict coronal mass ejections from the sun, which can fry our power grids.
Yes.
They're even modeling ice sheet friction, like how warm ocean water melts the underbelly of Antarctic ice shelves, uncorking glaciers, and accelerating sea level rise in places like Miami and Bangladesh.
It all comes back to that core philosophy.
Yeah.
You cannot understand the piece without understanding the whole.
But, I mean, simulating all of these intricate planetary gears, oceans, ozone, space weather, and ice, that creates a massive physical problem. You cannot run a wiki page of physics that is millions of lines long on a standard computer.
No, absolutely not.
You need a machine capable of doing the math for a quadrillion grid boxes in the blink of an eye.
And this brings us to the physical infrastructure that makes the intellectual commons possible in the first place. The supercomputers.
The dossier outlines the NCAR Wyoming Supercomputing Center, the NWSC, up in Cheyenne. It's funded by the National Science Foundation and the state of Wyoming.
Right.
And we see this rapid sequence of machines that trace the explosion of modern computing. It starts with Yellowstone in 2012, which ran at 1.5 petaflops. And the sources say Yellowstone was famous for enabling the CESM Large Ensemble Project, LENS.
Yes, LENS.
Why was LENS such a big deal, and why did they need a massive supercomputer to do it?
Because LENS solved the signal versus noise problem in climate science.
What do you mean by that?
Well, the Earth's climate is naturally very chaotic and noisy. You have random El Niños, random volcanic eruptions, decades where the ocean just absorbs more heat.
Yeah.
If you just run a simulation once from, say, 1920 to 2100, you get a graph of rising temperatures, but it's jagged. It's full of random noise.
So a skeptic could look at a single model run and say, oh, that heat wave in 2040 isn't global warming. It's just a random natural El Nino.
Exactly. So how do you isolate the human impact from the random butterfly effect chaos?
Right.
You use a large ensemble. You take the exact same starting conditions for the Earth in the year 1920, but you change the temperature of the atmosphere by a billionth of a degree, just an infinitesimally small perturbation.
The literal flap of a butterfly's wing.
Yes. Because the math of the atmosphere is inherently chaotic, that tiny fraction of a degree causes the simulation to develop completely different day-to-day weather over the next century.
Really? Just from a billionth of a degree?
Yeah. A storm hits New York instead of Boston. An El Nino happens in 1990 instead of 1995.
Yes.
So you run this parallel Earth 100 different times.
But all 100 Earths have the exact same amount of human CO2 being pumped into them.
Right. So you take all 100 jagged graphs of those different timelines and you average them together.
Oh, I see where this is going.
When you do that, the random natural noise, the chaotic El Niños and random storms, they just cancel each other out. They average to zero. And the smooth, undeniable curve that remains is the pure, isolated signal of human-caused climate change.
That is brilliant.
Yeah.
But running 100 parallel Earths simultaneously requires massive hardware, which leads us to the current behemoth at the center. Launched in July 2023, Derecho.
Derecho is an HPE Cray EX cluster. It is, frankly, a masterpiece of public engineering.
Let's break down the specs, because they are wild. It delivers nearly 20 petaflops of peak performance. Now, for the listener who doesn't build supercomputers in their garage, a flop is a floating point operation.
Right. Right. One mathematical calculation.
Like adding two long decimals together. A petaflop is 1 quadrillion of those calculations.
Yeah.
Every single second.
And Derecho does nearly 20 quadrillion calculations a second. It has roughly 3.5 times the scientific throughput of its predecessor, Cheyenne. It's built on nearly 2,500 compute nodes using AMD Milan processor cores.
But the hardware detail that really caught my eye in the sources is that Derecho includes 82 nodes dedicated to NVIDIA A100 GPUs.
The graphics processing units, yeah.
The exact same type of chips used to render high-end video games. Why does a climate model need graphics cards?
That is where the future of modeling is headed. Traditional CPUs are great at doing complex calculations in sequence. But GPUs are designed to do thousands of simple calculations simultaneously in parallel.
Okay.
This makes them the perfect architecture for machine learning and artificial intelligence.
Oh, wow. So they're bringing AI into the climate model.
Exactly. Remember those parameterizations we talked about?
Yeah.
The cheat sheets for how clouds form? Calculating those complex fluid dynamics equations for clouds in every single grid box takes up a massive amount of computing time. So, scientists are now training machine learning algorithms on incredibly detailed, small-scale cloud models.
I see.
Once the AI learns exactly how a cloud behaves under different temperatures and pressures, you can replace the heavy physics equations in the global model with the trained AI.
So instead of making the computer solve the complex math problem every single time a cloud forms, the AI just instantly recognizes the pattern and gives the answer.
Yes. It vastly speeds up the simulation, allowing scientists to run the model at even higher resolutions. And those NVIDIA GPUs on Derecho are specifically there to handle those new machine learning components.
It's just an incredible machine sitting on a 60-petabyte Lustre file system to store all the data. But the most important part of Derecho isn't the chips, is it? It's the access model.
Definitely.
The sources state that Direcco supports about 1,500 researchers at over 500 universities. And the way they get to use it is entirely foreign to the corporate tech world.
It is entirely merit-based. If a university scientist wants to run a complex wildfire simulation on Direcco, they don't buy server time with a corporate credit card like you would on Amazon Web Services.
Right.
They write a proposal. They outline the physics they want to test, why it will benefit the public understanding, and how many millions of core hours they need.
And a panel of peer scientists reviews it.
Mm-hmm.
If the idea is brilliant, you just get the keys to a 20 petaflop supercomputer for free.
Yes.
It completely democratizes the science. A young researcher at a small state university has the exact same access to world-class hardware as a massive, heavily funded Ivy League team.
And it goes even deeper into education. NCI hosts an annual CESM tutorial. They bring graduate students from all over the world to Boulder or connect with them virtually.
Yeah, the sources mention that.
They give them access to the code repositories on GitHub. They train them on how to write parameterizations. There are no licensing fees, no corporate paywalls. It's totally open.
It's like a global master-apprentice system. The grad student learning the code today is the lead scientist running a massive Direcco project 10 years from now. The code, the computer, and the community are all just fused together into this incredible public asset.
It's a very special ecosystem.
Which brings us to the final and, frankly, quite tense part of the source dossier. We have established this model is a miracle of human collaboration. But this public good is suddenly facing a severe structural threat.
Yes, according to the recent documents.
And again, just to reiterate for our listeners, we are drawing directly from the news reports and scientific publications detailed in our source stack from late 2025 and early 2026. We're looking at the structural timeline of this debate impartially to understand what the scientific community believes is at stake for this public commons.
Looking at the timeline, the crisis triggers in December 2025. Reports emerge indicating that the incoming administration, specifically through the Office of Management and Budget, plan to essentially dismantle NCIR. The dossier highlights a USA Today article reposted by Russ Vaught, which explicitly targeted NCIR, describing it as one of the largest sources of climate alarmism in the country.
Following that, the National Science Foundation, the NSF, which funds all of this, signaled to UCR that the management of the supercomputing center in Wyoming, the home of Direcco, was expected to transition to a third-party operator.
The scientific community's response was immediate and quite dire. The flagship magazine of the American Geophysical Union, EOS, published an article in January 2026 titled, "What Americans Lose If Their National Center for Atmospheric Research is Dismantled."
Wow.
The American Meteorological Society followed with similar pieces.
They framed the stakes explicitly around public safety, pointing out that in 2025 alone, extreme weather cost the U.S. 300 lives and $115 billion. And this all culminated in March 2026 when UCR filed a lawsuit to block the funding cuts and the transfer of the supercomputing center, resulting in a federal judge issuing a temporary block.
Right, so that is the current legal situation.
So that is the factual timeline of the legal fight. But I want to dig into the structural argument the scientists are making in these sources. Because if I'm just a casual observer, I might think, well, the code is open source. It's on GitHub. Who cares if they dismantle the central hub? The scientists can just download the code to their own laptops.
That is the crucial misunderstanding the scientific community is trying to address. A community model is not just a static file of code. The real threat is the loss of the steward.
I was trying to come up with a way to visualize this based on the reading. It seems like dismantling NCAR to save money or change management would be like looking at a massive, bustling public library, deciding to pave it over to build a more efficient parking lot, and saying, it's fine, the citizens took the books home, the words still exist.
That's a poignant comparison.
Because, yes, the physical books exist in random houses, but the library, the entire system that catalogs them, updates them, cross-references them, and provides a central hub for the community to actually utilize them, is destroyed.
That is exactly the dynamic at play here. The scientific papers in the dossier point to the immense, unseen labor required to maintain a commons. Think about the software engineers.
The staff at NCAR.
Yes. When Derecho was built with new AMD processors and NVIDIA GPUs, millions of lines of legacy code had to be completely rewritten and optimized to run on that specific new hardware.
Right. The university professors around the world aren't doing that. They are focused on the cloud physics.
Exactly. Or consider the working groups. If a team in Texas makes a breakthrough in how the land model handles soil moisture, and a team in Europe makes a breakthrough in how the ocean handles salt content, you cannot just blindly merge both into the code.
Right, because of the drift we talked about earlier.
Exactly. Someone has to run massive test simulations to ensure the new soil math doesn't accidentally crash the new ocean math when the whole system is coupled together. NCIR coordinates all of that testing.
And without that central hub.
The community model fractures. In software terms, it degrades into diverging forks.
Diverging forks.
Yeah. Texas has their version. Europe has their version. The models start producing different baseline results, and suddenly scientists can no longer reliably compare their research. The shared wiki page basically shatters into 1,000 isolated, incompatible notes.
Which brings up the pivot to privatization. The NSF signaled they wanted to transition the supercomputer to a third-party operator. If we look at this purely structurally, could a massive private defense contractor or a commercial weather corporation step in and steward this model instead of the public hub?
The consensus in the dossier from the scientific community is a very firm no, and it is not about technical capability. A private defense contractor absolutely has the engineers to run a supercomputer. The issue is the structural incentive.
It's the capitalist framework versus the commons.
Precisely. A commercial operator has fiduciary responsibilities. They exist to generate profit. They have an overwhelming structural incentive to monetize the infrastructure.
So they might start charging for access.
Exactly. They might start charging universities exorbitant fees for computing time on Direco, which immediately locks out the smaller state schools and kills the democratization of access we just talked about.
But even worse than charging for the computer is what it does to the code itself, right? If a private weather forecasting firm is running the model and a university researcher sends in a brilliant new parameterization for hurricane intensity,
then the private firm is structurally incentivized to take that code, keep it closed, and use it to make their own commercial weather forecasts better than their competitors.
wow. And the moment you introduce proprietary rights into the model, the entire social contract collapses.
It does. The thousands of university scientists around the world will simply stop contributing their free labor and brilliant ideas if they know those ideas are going to be locked behind a corporate paywall. The open collaborative engine that built the most complex simulation on Earth would just grind to a halt.
It really is a profound crossroads. We have covered an immense amount of ground today. From Warren Washington and Akira Kasahara building an atmosphere in a basement in 1963, to the elimination of flux adjustments, the integration of dying plankton, the discovery of how the ozone hole shifts ocean currents, right up to the 20 petaflop GPU clusters of Direco and the federal courts in 2026.
We really have traced the biography of a scientific masterpiece today.
So, to bring it all home, what does this actually mean for you, the person listening right now? If you lived in California during the brutal fire seasons of the 2020s, or if you live on the Gulf Coast, tracking the intensity of the next hurricane, your safety is inextricably linked to the physics calculated inside this machine.
It really is.
When civil engineers build a bridge or lay a new power grid, the stress tests they plan for are derived directly from the projections of this model.
The knowledge generated by CESM is the literal blueprint for how human civilization will navigate and adapt to an increasingly chaotic future. And the accuracy of that survival blueprint depends entirely on having thousands of the world's brightest minds constantly stress testing and improving it together, without borders or paywalls.
It proves that the most crucial tools for human survival don't have to be locked behind closed doors. Which leaves me with a thought I haven't been able to shake since reading these sources, and I want to leave it with you to mull over.
It's a big thought.
It is. We expect the most advanced, world-changing technology to be fiercely guarded corporate secrets. But this virtual Earth proves the exact opposite. If the most impossibly complex, accurate simulation of our chaotic planet was achieved not through ruthless corporate competition and proprietary patents, but through the radical cooperative sharing of thousands of minds in a public commons.
Then what else is possible?
Exactly. What other massive, unsolvable global challenges could we finally crack if we simply stopped treating human knowledge as property? Thank you for joining us and taking this deep dive today.